Hello, this is Lisa Seidman, and this is video 5 in a series of videos for biotechnology students. This video continues my discussion about the calculations involved in preparing solutions. In this video, I'm going to be introducing calculations where concentration is expressed in terms of molarity or millimolarity. So sometimes molarity gets a little bit confusing to people, but it's not going to be that hard if we remember that concentration is always a ratio, and we're talking about concentration over and over and over again in these videos. Concentration is the amount of solute over the total volume of the solution. Now, I just want to note that sometimes in chemistry applications, the denominator here might be a mass or a weight, but that's very unusual for us as biologists because we talk about things in water. So we're going to be talking about concentration always meaning the amount of solute per a total volume of solution. Let's start out by talking about the term a dozen. A dozen is an amount. A dozen means 12. So if I have a dozen eggs, I have 12 eggs. 2 dozen eggs, I have twice that many eggs. Now when we talk about molarity as an expression of concentration, we need to understand this term of mole. Now a mole is an amount, so just as a dozen means 12, a mole means a certain amount. It means 6.02 times 10 to the 23rd molecules. That's a kind of odd number. Where does that number come from? You may have seen it called Avogadro's number. So maybe it comes from somebody named Avogadro. Yes. Well, who was Avogadro? Well, good question, but not the topic for this video. If you're curious, you might try Googling that. What we do need to understand is that a mole is always the same amount of molecules. So just as a dozen is always 12, a mole is always 6.02 times 10 to the 23rd. 2 dozen is twice 12. 2 moles would be twice 6.02 times 10 to the 23rd molecules. Now that number is kind of strange, but don't worry, you do not need to memorize that number, not for the purpose of making solutions. Because if you're trying to measure out solute and you want a mole of it, you're not going to be counting out molecules. Nobody can see a molecule, and you certainly couldn't measure out 6.02 times 10 to the 23rd of them. So instead we use something we can measure out, which is weight. So let's talk about weight in terms of molarity. Because it turns out that for any substance, there is a particular weight or mass associated with Avogadro's number. So let's look at sodium chloride, for example, table salt, NaCl. If you take 6.02 times 10 to the 23rd molecules of NaCl, it will weigh approximately, or its mass to be more specifically, is 6.02, is 58.44 roughly grams. If you look at mercury, elemental mercury, that element is a very heavy element. If you had a mole of it, that is 6.02 times 10 to the 23rd molecules of it, you would have 201 grams. So for mercury, a mole weighs 201 grams. If you look at water, which is a relatively small compound, it's H2O, it's only 18 grams for 6.02 times 10 to the 23rd molecules. So for anything that might be our solute or anything we're thinking about, there is a weight or a molecular weight, what we sometimes call molecular weight, or if we're talking about a compound, the formula weight. That is how much a mole of it weighs. And that's the value that we're going to be interested in. So, moving along, when we talk about this term 1 capital M, the capital M means molar, M-O-L-E-R, molar, sorry, A-R. 1 mole of solute per 1 liter of water, or whatever the solvent is a 1 molar solution. So note here, a mole, this is an amount, and molar is a concentration, and I abbreviate concentration this way. So molar is a concentration, mole is an amount. Very important to keep those straight. A 1 molar solution contains 1 mole of solute per 1 liter. That's the definition. So if we're talking about salt, for example, sodium chloride, if you wanted to make a 1 molar solution of sodium chloride, you could, or you would, take 58.44 grams. That's approximate. It's a little bit more than that, but 58.44 grams of sodium chloride. You'd weigh it out, and then you would bring it to a final volume of 1 liter, and you would have 1 molar sodium chloride. And for any compound that you're interested in, you would take the formula, if you want to make 1 molar, for example, of calcium chloride, 1 molar of calcium chloride, you would take 111 grams of calcium chloride, you would weigh it out, and you would bring it to a volume of 1 liter, and you would have a 1 molar solution. And I want to note here that you may have learned in a chemistry class that you can find the molecular weight or the formula weight of a compound by adding up the atomic weights. So calcium chloride, you would add up the atomic weight of calcium, the atomic weight of 2 chlorines, and you'd add those together, you get 111 grams. And you could find those values on a periodic table. But in the real world, it's much better to look on the container, the chemical container, to find that formula weight. And there's a lot of reasons for that, one of which is that a lot of the compounds we will start to work with later on have very complicated chemical formulas. And so it's much more accurate to get the formula weight off of the bottle. Now I know you may or may not be able to see this in the video, but here's a bottle of potassium phosphate with all sorts of information that you might want. But one of the things on there is its formula weight, which is right here. And if you can't read it, it says 136.1. So if you wanted to make a 1 molar solution of this potassium phosphate, you know you would take 136.1 grams, weigh it out, and bring it to a volume of 1 liter, and you would have a 1 molar solution of the potassium phosphate. But what if you wanted to make not 1 molar, but what if you wanted to make 2 molar NaCl? So what would you do here? Well, okay, we know that to make 1 molar, you want 58.44 grams, and that's to make 1 molar. So you could set this up as a proportion. You could say, all right, if that's how much I need to make 1 molar, how much do I need to make 2 molars? Remember, we're always asking the question. These are all how much questions over and over again. How much do I need? How much do I need to make 2 molar? If you take 58.44, you cross multiply 58.44 times 2, and then you divide by 1, basically, you would find that question mark equals 116.88 grams. So that would be how you would make 2 molar. All right, fine. Well, let's suppose that instead of making 1 liter, you wanted to make 500 mils. Well, it's the same logic we could use again. We know that if 1 liter of sodium chloride requires 58.44 grams, then we can say if we want half a liter, remember 500 mils is half a liter, is going to require how many grams? And again, if you do the arithmetic, you would find that question mark equals 29.22 grams. So that's how much you'd weigh out, and you'd bring it to a volume of 500 mils. Okay, so we're using proportions as a method to do these calculations. But let's go to a situation where you want to make 300 mils of 0.8 tenths molar solution of calcium chloride. Here's our formula weight. Now, when we start to get into something like this, we can do that using proportions, and I'm going to show you how to do that, and then I'm going to show you a way that's more efficient than using proportions. So if you wanted to use proportions, you would do it in 2 steps. First, you would determine how much solute is needed to make 1 liter of 1/10 molar. So 1 liter of 1/10 molar. So we can do this again. If 111 grams is required for 1 molar, how many grams does it require for 0.8 molar? And if you do this cross multiply, you will find that the answer is it requires 88.8 grams. Okay? So then you have to go to step 2. And step 2 is determine how much solute is needed to make 300 mils. So we already figured out how much to make the 0.8. So we know that it takes 88.8 grams to make 1 liter, but we don't want 1 liter or 1,000 mils, which is a liter. We want 300 mils. So again, you say if it takes 88.8 grams to make 1,000 mils, how many grams to make 300 mils? If you do the math, you would come up with 26.64 grams. So you would do it you could do it in 2 steps. Now that works, and that's a perfectly respectable way to do it, but it's kind of slow. So in a situation like that, instead we use a unit canceling method. So we're going to call this unit canceling. So the unit canceling method, remember with unit canceling, your units have to all cancel properly. So if we look at this, solute required in grams. The grams in 1 mole, how many grams are in 1 mole, times moles per liter, times liters. Let's look. Do the units cancel? Yes. Liters, liters, moles, moles. It's going to leave us with grams, which is exactly what we want. Now there's another way to write this formula so we can see what each of those variables is. We can write it as formula weight, because the formula weight is how many grams of this substance are in 1 mole. Moles per liter, that's the molarity we want. We want 1 mole per liter. We want 0.5 moles per liter. We want whatever. You put it into here. And the liters required is just the liters required. So you can use this handy-dandy formula, and that is a lot faster. So for example, if I want to say, again, same question, how much solute is required to make 300 mils of an 0.8 molar solution of calcium chloride? The first thing you have to do is you have to convert 300 mils to liters, because that equation requires liters. You have to have this in liters. 300 mils divided by 1,000 is 0.3. That's how many liters you have. So now we're going to use our formula, our equation. We know that the units are going to cancel because I showed you that on the last slide. So we're going to take the formula weight, which is 111, times the molarity that we want, and that's going to be 0.8 times the number of liters we want. And if we do the arithmetic, it's going to come out to be the same, 26.64 grams. We know that the units will cancel and work out. That we got using the proportion method. This method, the unit canceling method, is much faster and it's much more efficient than doing the proportion method. So this is almost certainly what people would do. So I'm going to switch gears here, and I'm going to talk about this terminology. Now remember, this is repo buffer, which we've talked about several times, and we're finally getting to this nomenclature: 150 millimolars sodium chloride and 25 millimolar tris. So the little m, big M, stands for millimolar. It is related, millimolar, it's related to molarity, but it's got this milli in front of it. So let's think about what the milli means. What does it mean if we see that milli? Well, milli is a prefix that means 1/1000th. So a millimole is 1/1000th of a mole. So let's talk about NaCl. 1 mole of NaCl weighs 58.44 grams. So a millimole weighs 1/1000th of that, which is 0.05844 grams. So, given that we know that, and remember that's an amount, if we want to make a millimolar solution, we know that 1 molar NaCl is 1 mole, or 58.44 grams in 1 liter. So 1 millimolar NaCl is 1 millimole per liter of solution, or 0.05844 grams per 1 liter of solution. So a millimole is basically 1/1000th of a mole, and millimolar would be 1/1000th of that formula weight per liter. So how much solute is required to make 1 liter of a 1 millimolar solution of copper sulfate? The formula weight of copper sulfate is 159.61 grams. Well, let's take a look at that. Again, we can plug into the handy dandy formula. The formula weight, that would be the first thing we're going to plug in, times the molarity required. That is 1 millimolar. But now take a look. This says molarity required. It doesn't say millimolarity required. It says molarity. So we have to say that we have to remember that 1 millimolar is 0.001 molar. So here we're going to put in 0.001 molar. And then, of course, we're going to have our liters. And here it says 1 liter, so that's easy. So solute required in grams, 159.61 times 0.001 times 1, and we get 0.015961 grams. And you might think, okay, well, why would I ever be using millimolar? Why not just molar? Why do we ever wind up having to know that? And it's because when we're talking about a lot of the reactions in biotechnology, we do have solutes sometimes that are present in pretty low amounts. So 0.015961 grams is an amount you could weigh out in the lab. It's doable. It isn't a whole lot, and it's not going to look, it's not going to look like a lot of solute, but it can be done. And it wouldn't be unusual to be weighing out solutes in about these amounts, pretty small amounts. So now we get to a couple problems for you to practice with. So my suggestion would be that you could stop the video and you could try to do a couple problems just to test yourself. The first one is, how would you prepare 10 liters of 3/10 molar potassium phosphate? Formula weight is 136.09 grams. How would you prepare 500 mils of 5 millimolar sodium chloride with a formula weight of 58.44 grams? Okay, so go ahead and stop the video and take a look. Okay, let's start with the first one. Again, we have the same equation that we had before. This is our handy dandy formula. So again, we're going to substitute into it 136.09 times the molarity required, which is 0.3 times 10, because we want 10 liters. And it's going to equal 408.27 grams. And again, we would bring it to a volume of 10 liters. Now, just to show you that the units do cancel, let's just for fun, we have the formula weight means that there are 136.09 grams in 1 mole. And we want 0.3 moles per liter times 10 liters. And we remember that the units do indeed cancel for us, leaving us with an answer that will be in grams. Okay, so that's the first one. And here's the second question. How would you prepare 500 mils of a 5 millimolar solution of sodium chloride? And again, you can still use the handy dandy formula. Again, we put in the formula weight, which is 58.44. And we can put the units in here, grams in 1 mole, times the molarity that you want. But remember, the molarity is not 5, it is 0.005 moles per liter times, now again, we have to remember that's 500 mils, we have to convert that to liters, times 0.5 liters over 1. And we're going to get 0 0.1461 grams sodium chloride required, and we bring it to a volume of 500 mils. So that's it for this video. In the next video, I'm going to start to talk about solutions that have more than one solute, like that Reaper buffer, which had 5. So we're going to get to that in the next video, so stay tuned.